Hello students, let us start our today's session from the chapter Organic Compounds Containing Nitrogen, also called as the Amines chapter. So in amines we are going to discuss about the physical and chemical properties of amines. Let us discuss first of all physical property. The physical property, it deals about the physical state and odor, solubility as well as boiling point. So when we discuss about the physical state and odor of amines, the lower member up to the compounds having 3 carbon atom are found to be in gaseous state, colorless gaseous state, as well as they have ammonia like smell. Ammonia like smell is nothing but a pungent odor. But the higher members of amines having carbon atom 4 or more are colorless volatile liquid, at the same time they have fishy like odor. So when we discuss about solubility of amines are highly soluble in water. This is due to the formation of hydrogen bonding. How does it form hydrogen bond? Because water it has HOH structure and amine it has NH bond. So there is the formation of hydrogen bond between the oxygen atom of water with the hydrogen atom of amine, and hence the amines become soluble in water. But the higher members of amine, they are insoluble in water because of the hydrophobic nature of alkyl group. At the same time, when you compare about the solubility of amines with the alcohol, it is found to be alcohols are more soluble than amines. This is why, because we know the order of electronegativity of the 3 atoms, fluorine which is greater than oxygen, which is greater than nitrogen. The electronegative value of fluorine is actually 4 and that of oxygen is 3.5. For nitrogen it is 3.0. So the electronegative values of these 3 atoms, they do differ in their values, as well as they do have the difference in the formation of hydrogen bonding among themselves or even with water. So this is the reason alcohol, as the oxygen atom of alcohol, as it has 3.5, the electronegative value compared to nitrogen is much greater, and hence the strength of formation of hydrogen bond between the alcohol and water is much stronger compared to the amine with water. So solubility of alcohol is greater in water than amines. This is because the bond formation between the hydrogen bond formation between alcohol and water is much stronger due to its higher electronegative value compared to amines. When we discuss about the boiling point of amines, here the tendency to form intermolecular hydrogen bonding among the amines only determine the boiling point of amines. Primary amine, it has NH2 group. So this NH2 group is capable of forming 3 more hydrogen bond with 3 more amines. So every 2 hydrogen atom as well as the nitrogen atom that can able to make hydrogen bond with 3 more molecules, and successively the other amines also they proceed with the formation of hydrogen bond. But when we go to the secondary amine, as it has only the nitrogen and hydrogen as the functional group, this nitrogen able to make hydrogen bond with the 1 more molecule, and this hydrogen able to make another hydrogen bond with another molecule. So in the secondary amine, the NH, it has a tendency to make only 2 more hydrogen bond with amines. But in the case of tertiary amine, as this functional nitrogen has no hydrogen atom, and hence tertiary amines do not form hydrogen bond among the molecules. So due to the difference in formation of hydrogen bond, the intermolecular hydrogen bond among the primary, secondary and tertiary, it is found to be the primary amines have higher boiling point compared to secondary amine, which is than tertiary amine. At the same time, when molar mass of alkyl group increases, the boiling point of the compound also be increases. And the same case it is applicable even for aromatic amines. That's all the physical properties of amines. The next one, chemical properties of amines. Let us discuss the chemical properties of amines one by one. The first one is alkylation. This alkylation already we discussed in our preparation of amines. So in that case we said excess of alkyl halide is taken and the reaction will be proceeding until the formation of quaternary ammonium salt with ammonia. But here we have taken the primary amine. When this primary amine is treated with the excess alkyl halide, primary amine get into secondary amine to tertiary amine, and tertiary amine into quaternary ammonium salt. So in this reaction every hydrogen atom is being replaced by an alkyl group and hence RNH2 it becomes R2NH. So this hydrogen atom is combined with the halide atom of alkyl halide and it is removed as hydrogen halide. So here I have taken R group. The R group or even the alkyl group, you can take either methyl, ethyl, whatever it is. Suppose in place of alkyl R group, if I keep methyl, then it is methylamine. Methylamine, when it reacts with the methyl halide, it forms dimethylamine. And on another molecule of methyl halide, it forms trimethylamine. And one more molecule of methyl halide that makes trimethylamine into tetramethyl ammonium halide, a quaternary salt. The next one, acylation. Acylation reaction can be undergone by both aliphatic as well as aromatic primary amines and secondary amines. Tertiary amines do not undergo this reaction. This is why, because tertiary amine it has no hydrogen atom, and primary it has 2 hydrogen in amine group, secondary it has 1 hydrogen in its amine group. But in the case of tertiary it has no hydrogen and hence it will not undergo acylation reaction. So in this case both aliphatic, aromatic primary and secondary amine it may react with the derivatives of carboxylic acid, say acid chlorides, acid anhydrides and even with esters. But the reaction it follows nucleophilic substitution reaction. In this the nucleophiles are amine group behaves as the nucleophile because nitrogen carries the lone pair electron and the electrophile is the derivatives of carboxylic acid. Mostly these reactions are carried out in presence of a base. The base what we have taken must be stronger than the amines and hence these reactions are carried out in presence of pyridine. So the presence of pyridine that may neutralize the hydrogen chloride formed in the reaction and hence the equilibrium may push us towards the formation of amides. So in this case we used to get N-alkyl substituted amides we will get as the product. So let us find how the reaction proceeds. I have taken alkyl amine and this is acid halide. In this acid halide carbon oxygen, the oxygen is more electronegative. So it withdraws the electron from the carbon and hence the positive charge is developed at the carbon. So this electrophilic site is now attacked by the nucleophile. So amine is taken as nucleophile. As it donates its lone pair electron to the carbon, that makes bond between carbonyl carbon with nitrogen. So we can write RNH2 with the single bond of CCH3OCl. In this case, nitrogen carries the positive charge and oxygen carries the negative charge. So there would be a loss of hydrogen chloride among the molecule. So in this case, nitrogen being a positive charge, it withdraws the electron from the hydrogen and hence it becomes H+. Subsequently, it is removed with the halide ion making HCl. So when the halogen is removed, electron density of carbon will be decreased. The valency it goes only 3 and hence the negative charge on oxygen moves towards the carbon, therefore we are getting RNHCOCH3. So this is what the procedure that follows nucleophilic substitution reaction with acid halides or esters or even with anhydride. Same type of procedure only being followed for both aliphatic primary secondary as well as aromatic primary secondary amines. So let us find some example for this reaction. If I take ethyl amine, this is a primary amine. When it reacts with the ethanoyl chloride or you can say acetyl chloride. So here a molecule of hydrogen chloride is removed and in the presence of base. So I can write plus HCl. This HCl is neutralized by pyridine. So I am getting N-ethyl acetamide. Similarly, if I take primary amine, the aromatic amine aniline is taken. This you can make it reaction with anhydride. The first one I have taken acid chloride. So the next one I am taking anhydride. Anhydride in which this HCH3COO is being eliminated. CH3COOH. So this becomes the electrophilic site as it withdraws the electron. So this nitrogen atom of NH2 group may attack the carbon and hence we are getting N-phenyl acetamides. But in this case you may find acetic acid is formed as a product. But acetic acid is a mild acid as well as the N-phenyl acetamide also possess the acidic character because of the presence of NH group. So these do not react and hence the reaction do not require any base or anything. The next one, the both of them, the first two cases I have taken primary aliphatic amine and primary aromatic amine. The next case I have taken the secondary amine. Secondary amine that can have only one hydrogen with nitrogen. So that also can be treated with the acid halide. So minus HCl is removed. So we are getting C2H5N C2H5COCH3. In this case you find it is bonded with two molecules of ethyl. In the previous case, the nitrogen atom is bonded with only one alkyl or only one aryl. So the name is given N-alkyl acetamide because amide formula is NH2C double bond O. This is amide formula. In this, one of the hydrogen or both the hydrogens are replaced by alkyl group and hence we are saying these are N-substituted amides. So in this case, the nitrogen it has two ethyl group. So the name is N-N diethyl acetamide. So these are the examples of acylation reaction with aliphatic and aromatic amines. The next one, Schotten-Baumann reaction. This Schotten-Baumann reaction is a name reaction in which benzyl chloride is treated with aniline. So the reaction between aniline and benzyl chloride only termed as Schotten-Baumann reaction and no other reactions are named like this. The same Schotten-Baumann reaction we discussed in phenol also, where phenol is treated with acid chloride, we got ester. Similarly, here instead of phenol, aniline is taken with benzoyl chloride. Once again, HCl is removed. So we are getting N-phenyl benzamide. So the name of the compound is N-phenyl benzamide. Carbylamine test. This carbylamine test is actually taken for primary amines only because this test is used to identify the primary amine, whether aliphatic or even aromatic, both that answers for carbylamine test. Secondary or tertiary do not answer carbylamine test. And this carbylamine test is characterized by the foul smelling of the formation of isocyanide. So these isocyanide, they have a foul smelling from which we can identify the given amine is a primary amine. Actually, these primary amines are treated with chloroform and potassium hydroxide. This chloroform potassium hydroxide is the reagent taken for Riemann-Tiemann reaction where phenol is converted into salicylaldehyde. The same reagent chloroform and potassium hydroxide, when it is treated with aliphatic amine or aromatic amine, we will get the isocyanides of alkyl group or the aryl. So they produce a foul smelling. From the foul smelling we can identify the amines are primary. See how the reaction proceeds. This chlorine that can combine with the potassium. So there are 3 KCl. And it has 3 OH group. Those are combined with the 2 hydrogen with 1 hydrogen. There is formation of 3 molecules of water and 3 molecules of potassium chloride in addition to the alkyl or aryl isocyanide. The next reaction with the nitrous acid. Nitrous acid actually taken as the mixture of sodium nitrite and HCl, or else you can represent nitrous acid as HNO2. The structure of nitrous acid is HON double bond O. This is the OH group and it has one N double bond O group. So with this nitrous acid, the aliphatic amines, they give rise to the different products. Depends upon the primary, secondary or tertiary. Suppose if I take primary amine, ethyl amine is taken when it is treated with sodium nitrite and HCl, keeping the reaction temperature 0 to 5 degrees Celsius or 273 to 278 Kelvin. This forms ethyl diazonium chloride. This compound is called ethyl diazonium chloride, but this compound is highly unstable and hence immediately hydrolyzed to form ethanol as well as nitrogen and HCl. So we are getting ethanol, nitrogen and HCl. So the formation of ethyl diazonium chloride is unstable and hence it is given in the square bracket. Why it is unstable? This is why this nitrogen atom, it cannot be stabilized through resonance, as the alkyl diazonium salts unable to stabilize themselves by resonance. They are said to be unstable and hence immediately hydrolyzed by water to form primary alcohol and nitrogen. The condition is the product formed must be a primary alcohol from the primary amine. If I take secondary amine, that forms nitroso compound of yellow oily liquid. So when I take the diethyl amine from the nitrous acid, I am taking HONO2 just for our convenience. So in this nitrous acid, the hydrogen atom of secondary amine combines with the OH of nitrous acid. So there is a loss of water molecule and hence we are getting diethyl nitrosoamine. See that N to the nitrogen NO group is present. This NO group is called nitroso group. So this nitroso group, as it is directly attached to nitrogen atom, it is said to be N-nitroso diethyl amine. Or in the case of a tertiary amine, where it forms the salt-like structure. So here nitrogen carries the lone pair electron that can be given to the hydrogen atom of, what is that? Nitrous acid. So you can write this is as HNO2. So as it attracts the hydrogen atom of nitrous acid, that makes NH plus and NO2, that makes the anionic part. So the name is tertiary ethyl ammonium nitrite. So 3 times ethyl group is taken. So it is tertiary ethyl ammonium nitrite. The next one, Lieberman's nitroso test. In the place of secondary aliphatic amine, if I take aromatic secondary amine, so it is N-methyl aniline. When it is treated with nitrous acid, that may also form N-nitroso phenyl methyl amine. It is said to be Lieberman's nitroso test. So this is for the identification of secondary amine and the color of the compound is yellow only. Diazotization reaction. In diazotization, aniline is converted into benzene diazonium chloride. And this reaction already we discussed in haloalkanes and arenes under SAMACHEER reaction for the preparation of chlorobenzene or bromobenzene. So here the diazotization is carried out in presence of sodium nitrite and HCl at the temperature of 273 to 278 Kelvin, since the compound formed is highly unstable at room temperature. So this diazonium chloride, it becomes stable for the aromatic compound. At the same time, the diazonium chloride formed from aliphatic amine is highly unstable. The reason behind this is the benzene diazonium chloride is stabilized through resonance stabilization, but in the case of ethyl diazonium chloride, the alkyl group it has neither a lone pair electron nor the pi bond, and hence the nitrogen-nitrogen bond unable to make a resonance conjugation with the alkyl part. But in the benzene ring, the diazonium group, it can be in conjugation with the pi electron of benzene ring. This is the reason benzene diazonium chlorides are stable, but the aliphatic primary amine that forms diazonium salt is highly unstable. That's why they form primary alcohol. That's all the reaction of primary, secondary and tertiary amines with nitrous acid. Reaction with benzene sulfonyl chloride. Benzene sulfonyl chloride is also known as Hinsberg's reagent. This reagent is used to distinguish between the three types of amine: primary, secondary and tertiary. So primary amine, when it is treated with the Hinsberg reagent, there is a loss of HCl and hence we are getting N-ethyl benzene sulfonamide. Followed by treatment with the sodium hydroxide, the salt it becomes soluble. This is because the presence of hydrogen atom in this group that makes the compound strongly acidic and hence it is soluble in sodium hydroxide. When we take the diethyl amine, that is the secondary amine, here also we may find a loss of HCl between the Hinsberg reagent and the secondary amine. In this we are getting N-diethyl benzene sulfonamide. But this nitrogen atom, as it has no hydrogen, this becomes insoluble in alkali. When we have tertiary amine, the tertiary amine it contains no hydrogen and hence it doesn't react with the Hinsberg reagent, so no reaction. Among these three class of amines, the primary amine becomes soluble in alkali, but the secondary amine becomes insoluble in alkali, and that of tertiary amine becomes no reaction with the Hinsberg reagent. The next one, mustard oil reaction. This mustard oil reaction is also called as Hoffman's mustard oil reaction, and this is also taken as test for primary amine. Carbylamine test, one more test is Hoffman's mustard oil reaction. In this case, the primary amines are actually treated with the carbon disulfide. So when primary amine is treated with the carbon disulfide, that makes the compound like this. So we are getting CH3NH C double bond S with the SH. So this sulfur, it attacks one of the hydrogen from the amine, and the bond between nitrogen hydrogen it moves towards the electrophilic site. This is nothing but the sulfur is withdrawing the pi electron and hence it develops a positive charge over the carbon. So this electron that moves towards the positively charged carbon. So we are getting the product CH3NH C double bond is SH. This is called thiol. When it is treated with the mercury chloride, it decomposes to form methyl isothiocyanate. It is called methyl isothiocyanate along with mercuric sulfide and hydrogen chloride. Suppose if we have aromatic amine, two molecules of aniline is heated with carbon disulfide, there is a loss of hydrogen sulfide. So minus H2S. In this, When the compound is boiled with the concentrated hydrochloric acid, we will get phenyl isothiocyanate. Here this compound is actually thiourea. This thio means sulfur. Thiourea, in this both of the hydrogen replaced by the phenyl group, and hence it is diphenyl thiourea. That's all. The chemical properties of aliphatic amines as well as aromatic amines. Now we are going to see about the electrophilic substitution reactions of aniline. Electrophilic substitution reactions of aniline. This NH2 group is highly activating group. So the benzene that may undergo electrophilic substitution reaction more readily. So just like OH group, NH2 group is also activating the benzene ring towards the electrophilic substitution reaction. As well as this NH2 group being highly activating and also orthopara directing group. But because of the highly activating nature of NH2 group, we unable to get the desirable product. Usually they give a polysubstituted product, or undesirable product will also be formed. So let us discuss one by one. Halogenation reaction. When aniline is treated with bromine water, so it forms a 2,4,6 tribromoaniline. In this, the 3 hydrogen atoms which are at 2,4,6 position is being substituted by the halogen. So we are getting 2,4,6 tribromoaniline. This is also a white precipitate. So this is also giving a white precipitate just like phenol with the bromine water. Suppose if I want to prepare only one monosubstituted aniline, then the activating effect of NH2 group has to be protected by the acylation reaction. So to get monosubstituted product, NH2 group must be protected by acylation. So acylation can be done in presence of a strong base like pyridine, where the hydrogen chloride is removed and hence we are getting N-phenyl acetamide. Followed by bromination in presence of acetic acid, the para isomer, the hydrogen bromide will be removed. So we are getting para bromo acetanilide. Actually this can also be called as acetanilide, and followed by the treatment with either acid or a base, the amide group will be eliminated. So we will get para bromoaniline. So this is called acetanilide. This, if you have instead of CH3 C6H5 is there, that is called benzanilide. Okay, how this protection of amino group leads to the formation of monobromo substituted aniline. This is why, because after the acylation of the amino group, the lone pair of electron present on nitrogen atom gets in conjugation with the oxygen atom of carbonyl group. So that makes nitrogen with the positive charge, oxygen with the negative charge. So this moves like this. That's why the availability of lone pair electron on the nitrogen atom gets reduced. So the activity effect of the amide group becomes lower than that of that amine group. This is the reason we can able to get the desired product after the protection of amino group by acylation. The next one, nitration. When aniline is nitrated with the nitric acid and sulfuric acid at 288 Kelvin, though it is an orthopara directing group, a meta isomer is also formed in a substantial quantity. See that? Para isomer is about 51%, but meta isomer is 47%. Ortho isomer it is just 2% only. This is because when aniline is treated with the nitric acid in presence of sulfuric acid, the aniline it gets protonated to form anilinium ion C6H5NH3 plus. This is called anilinium ion. So as soon as it gets protonated, this anilinium ion being the meta-directing group, meta-isomer is also formed in the higher quantity compared to ortho-isomer. So that can also be protected by the formation of amide. So we can avoid the formation of meta-isomer by protecting amino group with acylation. So we will get acetanilide followed by treatment with the nitrating mixture. We are getting para-nitroacetanilide. This is on hydrolysis with the acid or a base. We will get para-nitroaniline. In all these cases, after the protection of amino group by the acylation, we unable to get orthoisomer. This is why, because this amide group, such a bulky group, so which would not allow the electrophile to attack the second position because of the steric effect, and hence probably we will get para-isomer rather orthoisomer. Sulfonation of aniline. When aniline is sulfonated with the concentrated sulfuric acid, it forms the salt-like structure of phenyl ammonium hydrogen sulfate. Phenyl ammonium hydrogen sulfate. Upon heating with to 453 to 473 Kelvin, that forms para-aminobenzene sulfonic acid. With respect to sulfonic SO3H group, the amino group is present at its para position. So it is para-aminobenzene sulfonic acid. It is generally known as sulfonilic acid as the major product. Okay. This sulfonic acid, as it has both the acidic group as well as the basic group in the same compound. This amino group being the basic in nature and the SO3H group that behaves as the acidic group. That's why they can transfer the proton among the acid and base. So we can get NH3 plus SO3 minus, and this molecule is said to be Zwitter ion. So at pH equal to 7, this molecule that behaves as a neutral molecule. Suppose if the molecule is less than pH 7, that behaves as an acid. So acids are proton donor. So this sulfonic group, it donates its proton to the NH2 group. So it makes NH3 plus SO3 minus. So when pH is less than 7, then this group will be predominantly present. When pH is greater than 7, NH3 plus that donates its proton to the SO3 group, and hence it becomes this sulfonilic acid. So sulfonilic acid is existing when pH is greater than 7, and when pH is less than 7, that ionic form of sulfonilic acid is only existing. The next one, Friedel-Crafts reaction. Friedel-Crafts reaction actually does not take place. This is why. Aniline is a base and the reagent aluminium chloride is a Lewis acid. Lewis acid that can withdraw the lone pair of electron possessed by the amino group, and hence that makes salt-like structure. So further reaction will be stopped by alkyl group or even the acyl group. So Friedel-Crafts reaction cannot be taken place in aniline. That's all the electrophilic substitution reactions of aniline. The another important concept of amines is the basic nature of amines. Already we have discussed about the acidic nature of alcohols and phenols and acidic nature of carboxylic acids. Now the basic nature of amines. So amines are generally basic. This is because the nitrogen that carries lone pair electron on its atom. So this lone pair electron that makes its electron donor. Electron donors are Lewis bases. So we can say amines are Lewis bases. So when do they react with the acid? Immediately it donates its electron to the proton, and hence they are forming salt-like compound. Alkyl ammonium halide is formed. Similarly, aromatic amines also being protonated with acid, so it forms aniline halide. So because of the formation of such compound where the nitrogen donates its proton, and hence we can say aliphatic as well as aromatic amines are Lewis bases. Moreover, from the alkyl ammonium halide, even the primary amines can be recovered by treating with the base. So that makes this alkyl ammonium halide behaves as an acid, and hence it reacts with the base to form once again amines and water along with sodium halide. So amines are actually water soluble. This is because able to make hydrogen bond with water, and at the same time they become insoluble in organic solvents. So this is the reason we can separate amines from the non-basic organic compounds, where those non-basic organic compounds becomes insoluble in water. So upon filtration, the amines can be separated from other organic compounds. Now let us find how amines react with water. So when amine reacts with the water we can write it as HOH, where the lone pair of electron on nitrogen is given to the proton of water. We are getting alkyl ammonium ion and hydroxyl ion. So this reaction actually it exists in equilibrium. This is because the amine is a weak base. Whenever the compounds are weak, there would be an existence of equilibrium between the reactant and that of product. So for this equilibrium reaction, we can write what is equilibrium constant. K equilibrium is the product of concentrations of product divided by product of concentration of reactant. Here the change in concentration of water is said to be negligible, and hence this taken as a constant. When water is multiplied with the K equilibrium, we will get another constant. It is known as the dissociation constant of base. B for base. So the dissociation constant of base Kb is given by the product of concentration of alkyl ammonium ion into concentration of hydroxyl ion divided by amine. For this Kb, we can write what is its pKb. pKb is the negative logarithm of Kb, that is the dissociation constant, or we can say pKb is equal to 1 by log Kb. So from this we can identify pKb is inversely proportional to Kb, and hence we can say how the basic nature of amines being calculated from their Kb values or the pKb values. So we can say larger the Kb or smaller the pKb, because both of them are inversely related. If Kb is larger, the pKb will be smaller, and hence the base is said to be stronger. This is the most important point. So whenever they are giving that substituted amines, we have to identify how the basic nature varies upon from one to another. So this basic nature of amines that can be explained on the basis of the three different effects called inductive effect, solvation effect and steric hindrance. Inductive effect, we are studying about alkyl amine. All alkyl groups are plus I group. So plus I group, what it will do? It pushes the electron towards the nitrogen atom. Solvation effect. Here the amine group that can easily be protonated. So it forms NH3 plus ion. So where they are, the molecules can be solvated when it is present in aqueous phase. And steric hindrance. The steric hindrance is based on the size of the alkyl group. We know methyl group is smaller than ethyl group, which is smaller than propyl group. So depends on the type of alkyl group present in the amine and the type of the inductive effect of the alkyl group along with solvation effect, we can discuss how far the basic nature of amines gets changed over the substituted one, that is the primary, secondary and tertiary. So let us find first of all ammonia versus alkane amines. Ammonia NH3 alkane amine, it has an alkyl group. So where when alkane amine is protonated, it forms N-alkyl ammonium. Alkyl ammonium ion is produced. At the same time, when ammonia is protonated, it forms only the ammonium ion. The difference of these two, simple. This alkyl ammonium, it has the R group known as plus I group. But in the ammonia, it has no plus I group. So the presence of alkyl group, what it will do? Being plus I, it releases the electron towards the nitrogen atom. Already the nitrogen, it carries the lone pair electron. Now alkyl group also give away its electron towards the nitrogen, and hence the availability of lone pair electron over this nitrogen atom becomes much higher, and hence immediately that can abstract the proton. But in the case of ammonia, it has no plus I group, only the presence of lone pair electron tend to attract the H plus ion, and hence we can say alkane amines are stronger bases than ammonia. So we can say that alkane amines are stronger bases than ammonia. So it can be given when these amines are in the gaseous phase, there the tertiary amines greater than secondary amine, which is greater than primary amine, which is than ammonia. In this case, the number of alkyl group goes on decreasing from tertiary to ammonia. So in tertiary amine, there would be 3 alkyl group, all of them are plus I. All of them has to release the electron to nitrogen, and hence the electron density of nitrogen will be much higher compared to secondary or primary. So we can say in the gaseous phase, the condition is in the gaseous phase alone, tertiary amines are stronger bases than secondary amine, which is then primary amine than ammonia, due to the plus I effect of alkyl group. Now suppose if these alkane amines are in the aqueous phase, here the entire order of the stability will be changed. This is why, because the aqueous phase, the protonated ammonium, alkyl ammonium ions gets solvated by the water molecule. When we have primary amine, see that after the protonation, primary ammonium ion, it has 3 hydrogen atom. So all these 3 hydrogen atom can make hydrogen bond with the 3 moles of water. But in the secondary alkyl amine, after protonated, it has only 2 hydrogen, so that it can make solvation with 2 molecules of water. But in the tertiary amine, after the protonation, it has only 1 hydrogen, that it could make only 1 hydrogen bond. So the solvation effect of primary amine is much greater than that of secondary amine, which is then primary amine. So we can say the stability of primary amine is much stronger in its aqueous phase than the secondary or the tertiary. At the same time, if at all the size of alkyl group is larger, then its solvation effect will be smaller. So if bulky group is present, that becomes less solvated. So based on the solvation effect, we can say primary amines are more basic than secondary or than tertiary. But not only the solvation effect determines the basic nature, besides that we have to consider the plus I effect of alkyl group also. And moreover, I said bulky group that provides a steric effect. So though in aqueous phase, the stability, the basic nature of amines are further explained on the basis of inductive effect as well as the steric effect. So in this case, Suppose if you have that ethyl group in its amine, we can say the diethyl amine is greater than triethyl amine, which is greater than ethane amine greater than ammonia. So in this secondary amine, it has the solvation effect as well as it has two plus I group CH3, CH2. So number of plus I group increases, so it increases the electron density on nitrogen atom. When you go to the tertiary amine, besides the solvation effect, though it is solvated less readily, but the presence of 3 alkyl group that increases the electron density on nitrogen atom, and hence when ethyl group is present, then triethyl amine becomes stronger than the primary amine. In this primary amine, here solvation effect is maximum, but inductive effect is minimum. That's why we are having the order of basic nature for the ethane amine. Diethyl amine is greater than triethyl amine, which is greater than ethane amine and ammonia. Now, let us have the other one where instead of ethyl group, we are going to take methyl group. So, methyl group, its plus I effect is less, as well as the size of the group is also less. So in this, the solvation effect plays the major role than the inductive effect. So we can say that this methyl group, as it is present twice the time, inductive effect is maximum. And the solvation effect is also in between of primary and tertiary. So the solvation effect is compensated by the inductive effect, and hence the dimethylamine is stronger base. When we go to methane amine, here the solvation effect is more pronounced than inductive effect. That's why primary methane amine becomes stronger base than the trimethyl amine. So in this case, though it has plus I effect greater, solvation effect is minimum. That's why in the case of methyl substituted amine, secondary amine stronger than primary amine than tertiary amine, which is than ammonia. But in the case of ethyl substituted amine, here inductive effect that plays the major role than the steric effect as well as the solvation effect. So you can say secondary ethane amine is greater than tertiary ethane amine, greater than ethane amine, greater than ammonia. So that's all the basic nature of aliphatic amines only. Now we have to discuss about the basic nature of aromatic amines. Basic nature of aromatic amines. So when we compare the basic nature of aniline versus ammonia, in aniline the NH2 group is directly bonded to sp2 carbon atom, and this ring is electron withdrawing group. So, the lone pair of electron present on nitrogen atom can be effectively withdrawn by the benzene ring. So, the movement of electron takes place and hence this electron comes out. So, you may find a positive charge is lying over nitrogen atom, and this negative charge is further stabilized through its resonating structure. So, we are getting the possible resonating structure. Though this aniline is much stronger, that means more resonating structure, so greater the stability of the aniline, but it has no lone pair electron over the nitrogen after its conjugation. So because of the non-availability of lone pair electron on the nitrogen atom of aniline makes it less basic than ammonia. So we can say aniline is less basic than ammonia because of its non-availability of lone pair electron and it is in conjugation with the benzene ring. Now let us compare the basic nature of aniline with the anilinium ion. Anilinium is formed upon the protonation of aniline, so we are getting anilinium ion. In this anilinium ion, it may find only two possible resonating structure. Just the position of the pi bond gets altered. So compared to the number of resonating structures of anilinium ion with the aniline, it is found that aniline is more stable than anilinium ions. But though both of them, aniline as well as anilinium ions, are less basic than ammonia. Basic nature of substituted aniline. Usually electron donating group increases the basic group because it releases the electron towards the benzene ring and hence the electron density of nitrogen increases. But in the case of electron withdrawing group, that decreases the electron density of ring itself and hence the electron density on nitrogen atom also decreases. So when we compare the presence of electron donating group and the electron withdrawing group in the benzene ring, we can have, though all these substituents are there, ammonia is more basic, which is then the methoxyaniline, or it is greater than aniline and it is para-nitroaniline. That's all the basic nature of aromatic amines. The next topic from amines is benzene diazonium salts. Besides that, we have to see about cyanides and isocyanides. Let's see first of all diazonium salts. Diazonium salts are generally represented as ArN2X-, where Ar is an aryl group and N2 plus is a diazonium group and X-, that could be a chloride ion or a bromide ion or bisulfate ion or even tetrafluoroborate ion. So in this benzene diazonium chloride, which is stable, but for at room temperature it is not stable. So as soon as it is prepared, it has to be used for further reaction. At the same time, alkyl diazonium chloride are highly unstable and they will be hydrolyzed to alcohol. Already we discussed, because of the absence of resonance in alkyl diazonium salt, they become unstable. Okay, let us see about the preparation of benzene diazonium salt. Several times we discussed about this. So the treatment of aniline with sodium nitrite and HCl, that gives rise to HNO2. That gives rise to HNO2, nitrous acid. Between 0 to 5 degrees Celsius, it forms benzene diazonium chloride and sodium chloride with water. So what are the physical properties of benzene diazonium chloride? Actually, these diazonium salts are crystalline in nature as well as colored one. At the same time, this compound, only the benzene diazonium fluoroborate is water insoluble, but it is stable at room temperature. Only the diazonium salt that is stable at room temperature is benzene diazonium fluoroborate. All other benzene diazonium salts are unstable at room temperature. So this benzene diazonium chloride actually water soluble. When it is formed with the water, it is converted into phenol. Okay, and then this benzene diazonium salt neutral to litmus. That means they are neither acidic nor basic, but they do able to conduct electricity because of the charges N2 plus and Cl minus. So they do conduct electricity. What are the chemical properties of benzene diazonium salts? This benzene diazonium group, it has two different reactions. One is the reaction in which the diazonium group is to be replaced by some other group. The other one, the reactions in which the diazonium group is retained. So let us see first of all the replacement of diazonium group from the diazonium salt. The first reaction is reduction. Diazonium salt that can be reduced by either ethanol or with hypophosphorus acid and water. H3PO2 is hypophosphorus acid. When it is undergoing treatment with the ethanol, this benzene diazonium chloride is reduced to benzene, where ethanol is oxidized to acetaldehyde. In addition to that, nitrogen and HCl are removed. At the same time, when it is reduced by hypophosphorus acid and water, once again diazonium salt is reduced to benzene, Hypophosphorus acid is oxidized to phosphorus acid along with the nitrogen and HCl. The next one, replacement by OH group. This is done simply by warming with the water. The diazonium group will be eliminated, chlorine will be eliminated as hydrogen chloride, so we can get a C6H5OH. Phenol is formed. The next one, replacement by NO2 group. For this, first of all, the diazonium chloride is converted into diazonium fluoroborate. So, this is done by treating with the HBF4, hydrofluoroboric acid, in which the hydrogen chloride is removed, and hence we are getting benzene diazonium fluoroborate. When it is heated with the sodium nitrite in presence of copper, it forms nitrobenzene, boron trifluoride, nitrogen and NaF. The next one, replacement by fluorine. See, fluorine that cannot be directly attached to the benzene ring or even the aliphatic compound, but when we have diazonium salt, we can readily prepare fluorobenzene. That can be done once again by treating diazonium salt with the HBF4, HCl is removed. So, we are getting diazonium fluoroborate, in which subsequently boron trifluoride and nitrogen are removed. So, we are getting fluorobenzene. The next one, replacement by iodine. Fluorine as well as iodine that cannot be directly added to the benzene ring, but can be done in terms of the formation of benzene diazonium chloride. So, that can be done simply treating with the potassium iodide. Diazonium salt simply treated with the potassium iodide, where nitrogen is expelled, potassium chloride is formed. So, we can get C6H5I, iodobenzene is formed. The next reaction, preparation of biphenyl, in which benzene diazonium chloride is treated with benzene in presence of sodium hydroxide. This reaction is said to be Gomberg reaction. So, in this the HCl is removed, nitrogen is expelled out as gas. So, we are getting C6H5, that is called biphenyl. The next reaction is replacement by carboxyl group, COOH. That to be done, first of all, converting this diazonium chloride into diazonium fluoroborate, followed by treatment with the ethanoic acid, that is acetic acid. One of the fluorine with the methyl group is left as fluoromethane. So, C6H5COOH, benzoic acid is formed. In addition to that, BF3 and nitrogens are produced. SAMACHEER reaction. Benzene diazonium chloride, from which we can able to prepare chlorobenzene, bromobenzene and cyanobenzene. That can be done by treating with the copper 1 chloride with the HCl, it gives chlorobenzene. Copper 1 bromide with the HBr, it gives bromobenzene, or with the copper cyanide, it gives cyanobenzene. So, in all these cases, the nitrogen gas is expelled along with the formation of HCl. Gattermann reaction, just similar to that of SAMACHEER reaction, but in this case, instead of copper 1 salt, we will take copper metal with the HCl or copper metal with the HBr. Here also, when you take HCl, we will get chlorobenzene, or when we take HBr, we will get bromobenzene. So, here the halides are converted into copper 1 chloride or copper 1 bromide. The next set of reactions, in which the nitrogen group is being retained. So, we can say retention of diazonium group in the reactions. So, first one, formation of hydrazines. Hydrazine C6H5NH, NH2. So, when this diazonium chloride is reduced by either stannous chloride and HCl or with the sodium sulfite, this N triple bond N is reduced to NH, NH2. So, it is called phenyl hydrazine. And other reaction is coupling reaction. This coupling reaction is one of the most important reaction by which the different colored dye can be produced. And also we can identify this is the test to distinguish between phenol and the aniline. because both phenol as well as aniline they form white precipitate with bromine water, but at the same time with the diazonium salt they give rise to different colored dye. So coupling reaction can be used to identify the presence of phenol or aniline. So when this reaction carried out, actually it takes place in presence of sodium hydroxide. This is why, because the byproduct formed is HCl that to be neutralized by the sodium hydroxide. So when benzene diazonium chloride treated with the phenol, the para position of hydrogen combines with the hydrogen, so there is minus HCl forming para hydroxyazobenzene, an orange colored dye. At the same time, when benzene diazonium chloride is treated with the aniline in presence of a base, once again the HCl is removed. So we will get para aminoazobenzene and yellow dye is formed. At the same time, when benzene diazonium chloride is treated with para-cresol. So in this case, when both para positions are occupied by OH group as well as the methyl group, the next to the position OH, the hydrogen is being substituted by the diazonium group. So we will get, so we can numbering, this is first position, second position, third position, fourth position. To the second position we have azo group, and the fourth position methyl group is present. So we can write 2-phenyl azo, 4-methyl phenol. That's all the chemical properties of benzene diazonium chloride. So this benzene diazonium chloride is such a wonderful synthetic reagent from which all the derivatives of the aromatic compounds can be prepared. The next topic of this chapter is cyanides and isocyanides. Cyanides are alkane nitriles, isocyanides are either alkyl isocyanide or alkyl carbylamine. So the IUPAC name, common name, both of them are almost same. They have given nitriles only. Suppose if I have 2 carbon, it is called CH3CN. So it is ethane. As it has the cyano group, it is called ethane nitrile. Suppose if the compound has more than one substituent, where the cyano group becomes the prefix of the compound, so the carboxylic group has the preference. So it is called 1, 2, 3, 4. So third position it has the cyano group. So the name is 3-cyanobutanoic acid. And in isocyanides is either called as alkyl isocyanide or alkyl carbylamine. For example, if I have CH3CH2NC, it is ethyl isocyanide, or in IUPAC name it is called ethyl carbylamine. Similarly, C6H5NC, it is phenyl isocyanide, common name, or its IUPAC name will be phenyl carbylamine. Just an example only taken, the rest you can find it in reader. The next one, preparation of alkyl cyanides. Actually, alkyl cyanides are prepared from the first chapter, nucleophilic substitution reaction. So when alkyl halide is treated with alcoholic potassium cyanide, we will get alkyl cyanide and potassium chloride. So in this case the KBr is removed, so cyano group is substituted to the place of bromide, so we are getting propane nitrile, or it is ethyl cyanide. The next method is dehydration. A water molecule that can be removed from either amides or from oxime. So when we take amide, when it is heated with the phosphorus pentoxide, there is loss of water molecule, so we will get CH3CN. Or if we take acetal dioxide, here also this H and OH is being removed, so we will get acetonitrile. The next one, from ammonium salts. These ammonium salts are formed by treating carboxylic acid with ammonia. So I have taken ammonium acetate. First of all, when it is heated, there is a loss of water molecule, so it forms amide. Once again amide. So the amide followed by heating with the dehydrating agent P2O5, we are getting cyanides and water. The next one from Grignard reagent. Grignard reagent, here I have taken methyl magnesium chloride. It is simply on treatment with the cyanogen chloride. So here MgCl2 can be removed, so you can get CH3Cn and MgCl2. Okay, the next one, physical properties of cyanides. The lower members are having pleasant smelling liquids, the higher members are crystalline solids, and these cyanides are actually poisonous, but the boiling point is greater than that of acetylene. Why it is compared with the acetylene? Because acetylene formula is CH triple bond CH. In this case, we have a carbon-carbon triple bond. It is analogous with CH3 C triple bond N. So we are saying the two compounds are analogous to each other. So here, due to the greater polarity of the CN group, nitriles have higher boiling point than acetylenes. Chemical properties of cyanides. First property, hydrolysis. We know well, cyanides, they may undergo complete hydrolysis to form carboxylic acid through the formation of amide. So the first step undergoes partial hydrolysis, the second step it undergoes complete hydrolysis. So hydrolysis of cyanide, it gives rise to carboxylic acid. And reduction, where CN group is completely reduced to CH2 NH2, so we will get primary amine. Condensation reaction. Here we have two types of condensation reaction. One is called Thorpe-Nitrile condensation. In this case, two molecules of nitrile that undergoes condensation in presence of sodium and ether. Here the cyano group of one molecule that gets condensed with the compound having alpha hydrogen. So this is the functional group. Attached carbon is alpha carbon that has hydrogen. So this alpha hydrogen and the CN group gets condensed to form C double bond NH. So we will get 3 imino 2 methyl. First position, second position, third, 4, 5. So 3 imino 2 methyl pentane nitrile is formed. So both of the condensation reaction possible where the compound is having alpha hydrogen. The other one is Levin-Hassler acylation reaction. In this, the ester on reaction with the nitrile, it forms the product alcohol followed by ketone nitrile. See, 1, 2, 3, 4, 5. So in the third position we have the keto group. So it is called 3-ketopentane nitrile. That's all the chemical properties of cyanides. Here one or the other reactions already we have discussed in the previous chapters. So the same thing is getting repeated once again. The next one, isocyanides. Isocyanides that can even be prepared by carbyl amine reaction. Just now we saw that is the test for primary amine. So when it is treated with the chloroform and potassium hydroxide, it forms an offensive odor, or we can say that foul smelling isocyanide. Then from alkyl halide. That cyanide is prepared from alkyl halide by treating with the alcoholic potassium cyanide. Here, when we treated with the silver cyanide, we will get isocyanide. Cyanide and isocyanide are ambident nucleophile. So when we have the different compound, we will get the different product. The next one, from N-methyl formamide. This is called N-methyl formamide. When it is treated with the phosphorus oxychloride in presence of pyridine, there is once again loss of water molecule. So we will get isocyanide. The physical properties of isocyanide. Actually, isocyanides are still high poisonous than cyanides, and they have unpleasant smelling as well as volatile liquids, but their melting and boiling points are lesser than cyanide. This is because isocyanides are less polar in nature. Chemical properties of isocyanides. The first property is hydrolysis. Cyanide on hydrolysis we got amide and carboxylic acid, but in isocyanide it forms amine and carboxylic acid. So this N triple bond C gets broken, so we are getting CH3NH2 and HCOOH. So formic acid and methylamine is formed. The next one, reduction. Cyanides on reduction, they gave primary amine. Isocyanides on reduction gives secondary amine. So we are getting N-methyl methanamine, or we can say dimethylamine is formed. The next one, isomerization. We said cyanides are isomeric with isocyanides. So when isocyanide is heated to 250 degrees Celsius, it gets isomerized to nitriles or cyanides. Addition reaction. So in this case, actually the triple bond cyanide group is C triple bond N with alkyl. But in isocyanide, the nitro group, it donates its one of the pair electron towards the carbon atom. So actually carbon carries one pair of electron, the other two electron gets shared with the nitrogen atom, and nitrogen, it has one more pair electron, lone pair, that is what given to carbon. So this is what the structure of isocyanide. Such structure of isocyanide that favors the addition reaction with the most electronegative atoms like halogen, oxygen, and even with sulfur. When we have halogen, addition reaction actually takes place only upon nitrogen and carbon. So we will get the dihalo derivative is formed. Or when it is treated with the sulfur, it forms alkyl isothiocyanate, or with the oxygen, it forms alkyl isocyanate. So this isothiocyanate and isocyanate are also the isomers of cyanate and thiocyanate. So these two are thiocyanate, cyanate. This is the isomer of isothiocyanate. This is the isomer of isocyanate. That's all the chemical properties of isocyanides. Okay students, this chapter got over. So we completed organic compounds containing nitrogen. So in this chapter we studied about nitro compounds, amines, diazonium salts, cyanides as well as isocyanides. Okay students, we have completed organic chemistry for class 11 as well as class 12. Hoping you will understand all the concepts in better way. And we will see the next class. Until then, bye bye.